Okay. All right, we'll go on and get started. So thanks everyone for coming today. Welcome to the second session of Build. My name is Bennett Sorbo. I'm a program manager on the Direct3D team, and I'm here today to present what's new in Direct3D 11.2 for Windows 8.1. So over the past year, we've spent a lot of time looking at how we can make Direct3D better. And what we found is because Direct3D is defined by its performance, the best way to make Direct3D better is to improve the performance of Direct3D. So we spent a lot of time looking at existing apps in the marketplace, how people are using Direct3D, what the critical paths are, what we can improve in the runtime, what core improvements we can make to benefit existing apps. But secondly, we also worked with hardware partners. We tried to find out what new APIs we can create that allow apps to drive existing and new hardware in new ways to render more efficiently and to render in new ways. So today, we're going to give a quick overview of what Direct3D is, what our goals are for it, and how we're moving those forward in Windows 8.1. We're going to give a quick overview of the core improvements to Direct3D, changes we've made at the runtime that apps will benefit from just by moving to Windows 8.1 with little or no changes to the app code. We're then going to go into leveraging new features, leveraging new APIs and new functionality in the runtime that lets apps render in entirely new ways. Some really cool stuff there. And then we'll finally give a quick summary and point to other kind of resources for Direct3D and other talks we're giving today. So administratively, I'd actually ask, keep track of any questions that you might have. We'll have time at the end for questions, but we want to make sure we get through everything today. Evaluations are also available for all the sessions we're giving. So if you have any feedback or any pointers, stuff you'd like to see more of, please definitely fill that out. And finally, this talk is geared towards people who are already familiar with Direct3D. It assumes a general level of knowledge with the API. So those are the people who will get the most out of this. So going into the overview, what is Direct3D? What are our goals with it? So the purpose of Direct3D is to be a high-performance graphics API, an API that apps can use to directly access the graphics hardware in a low-level, performant way. We try to get the API out of the way and let the app access the power of the hardware in the most performant way possible. But also, it's to be able to target an extremely wide variety of hardware. So you can write one app using the Direct3D API that targets graphics hardware from a variety of hardware manufacturers, but also hardware from a variety of power levels, everything from a power-efficient SoC platform all the way up to really powerful discrete GPUs. And it's an API that you can use in a variety of platforms. So you can take Direct3D code from a Windows Store app, easily move it to the Windows desktop environment. When you write a Windows Phone app, you can take the Direct3D code, easily move it to there. If you're an Xbox developer, you can easily use your Direct3D code on that platform as well. So it's an API that's very performant, but is also designed to work across a variety of platforms. So what's new in Direct3D for Windows 8.1? How are we expanding on that? So as I said, the focus for the release was performance. We've made a number of core improvements to the API. Existing APIs are getting faster. We're making a lot of really great changes there. But beyond kind of the core improvements to the runtime, there are also new APIs, new functionality available. And that's what we're calling Direct3D 11.2. So it's a new iteration of the Direct3D API. It's backwards compatible with all existing Direct3D apps. When you want to use new APIs, you simply include new header files, use new interfaces. If you take an existing Windows 8 app and move it to Windows 8.1, it'll compile and run just great, and you'll benefit from the core improvements. But when you want to move to the new APIs, it's as easy as including new header files and dropping in new interfaces. So an important point to note about compatibility is that while we're incrementing the version number 11.2, we're bringing all the new APIs and new functionality to existing feature levels. So in Windows 8, we introduced DirectX 11.1, and we introduced an 11.1 feature level. So now we're introducing a new 11.2 API, but bringing the functionality to existing feature levels. So you'll see features from feature level 9 all the way up to feature level 11. And this lets you use the power of hardware that's already out in the marketplace today. Okay, so we'll go on and jump into the core improvements, what we've changed in the runtime that apps are going to benefit from with few or little changes. So the first core improvement is on new drivers, everyday operations are faster. In particular, on feature level 9, getting data to and from the GPU is dramatically faster. The Update Sub-Resource API has been optimized to double the speed of GPU uploads. For any given resource size, you'll now see half the CPU cost of moving that data to the GPU. That's true for a 4 kilobyte resource or a 4 megabyte resource. You'll see great scaling with that. It's also true for staging resources. Copies between default and staging resources are now literally twice as fast, and that's true for all resource sizes, and it's a really great improvement if you're using Update Sub-Resource to update a vertex buffer, or if you're using staging resources to get data back from the GPU and read it on the CPU. So we're really excited about that. Going beyond feature level 9, we've also improved the present API itself. We're now spending less time in the present API, dramatically less time in the present API, so that apps can spend more time doing the real rendering work and have more time in a frame to do their rendering operations and still present in time to hit 60 frames a second. So everyday operations are faster. Secondly, we're introducing existing functionality to new feature levels. So in Windows 8, we took shadow buffers, which were previously exclusive to feature level 10, and made them optional for feature level 9. And that allowed apps to make use of shadow buffers and all their capabilities on the widest variety of hardware possible. With Windows 8.1, we're doing the same for instancing. So today, instancing is a great feature that lets you reduce the amount of vertex data you need to send to the GPU if there's kind of commonalities between the geometries that you're rendering. But it's exclusive to feature level 9.3 and higher. So in Windows 8.1, we're now making it optional for feature level 9.1. We're introducing a new check that apps can check for using check feature support to determine whether instancing is available. So the new decision path can be, is feature level greater than or equal to 9.3, or is 9.1 instancing available? Third, we've made some really great reductions in frame latency. And frame latency we're defining as the time between calling present and the time before that screen showing up on the display. So depending on an app's workload, you'll actually see up to a frame reduction in the amount of time a frame is queued for execution before it shows up on the display. We made some really great changes to the graphics scheduler that enable that. But we think it's actually a really great change to reduce latency in apps. Going on, there's a new API we're introducing called DXGI Device 3 Trim. And the purpose of this API is to allow an app to reduce its memory usage when it is idle. And the reason it's important for an app to reduce its memory usage when it's idle is in the Windows Store environment, you can have many apps loaded into memory at one time. Even if you have one app visible on the screen, the system tries to keep as many apps in memory as possible so that if the user wants to switch back, it's a very quick, seamless switch and you can just open it right up. So the way that happens is if the system begins to run out of memory, the system will start to look at, okay, which apps are taking up the most memory, which can I terminate to make sure the system doesn't run out of memory. So if an app is lowering its memory usage when it's idle, when it's hidden from the user, it actually increases the chances of it staying in memory and being responsive when the user switches back to it. So the way this works is when an app is rendering, the graphics driver will allocate memory kind of behind the scenes that it needs to perform rendering operations. And it'll persist this memory between different frames. And it's really important to allow, for great performance, you don't have to reallocate memory constantly. But when the app is hidden, when the app is no longer rendering, that memory kind of sits around as a dead weight. So the Trim API tells the driver that, hey, the app is going to be idle for a long period of time. The driver should go on and release that memory. And the way the API works is, that's it. There's no further action necessary from the app. When the app starts to render again, the driver will begin to automatically repopulate the internal driver memory. There is no visible change to the app beyond that point. So it's great for the app. Again, you increase the chance of your app staying in memory. You reduce overall system resources. But it's also better for other apps. You can keep more apps in the system at the same time. And for that reason, we're actually requiring all apps to call the Trim API on the suspend callback. So what you'll see is when you submit an 8.1 store for app certification, we're introducing a test that we make sure that the app calls trim on any D3D device the app directly creates. Okay, so those are the core improvements that we made, making existing APIs faster, bringing new functionality down to existing feature levels, and introducing new ways to save memory during idle. So let's go into the actual new APIs and new functionality that's available in Direct3D 11.2. So we're going to go over 5 features today, and on each of the features, you'll see a key at the bottom right-hand corner that lets you know when a feature is going to be available on a particular platform. You'll either see for a given feature level, it's guaranteed to be supported. You'll see you might have to check for support using check feature support, or the feature just might not be available at that feature level. So the first feature we're going to talk about is hardware overlay support. We're introducing new APIs that allow games to take advantage of fixed function hardware overlays that are starting to become present in a lot of mobile SoC platforms. Some really cool stuff there. The second, we're going to go over a new API, a new functionality that allows apps to really efficiently change the behavior of shaders at runtime that we're calling shader linking. Third, we're introducing the ability for apps to more directly access GPU memory. This is really great for compute scenarios when maybe you don't want to do an extra copy before you can read stuff back on the CPU. We're going to allow the CPU to directly access GPU default memory in this case. Fourth, we're introducing a new low latency API that apps can use to optimize their rendering setup for low latency. Coupled with the earlier kind of core improvement change, it's actually possible now to get less than 1 frame of latency between rendering your code and presenting that to the screen. And we'll show a demo of that. It's pretty cool. And fifth, we're going to give a quick summary of what tiled resources is, what scenarios it can be used for, how your app can take advantage of that. And we'll kind of point you to the dedicated session that we're giving on that, which immediately follows. We're going to go into a lot of detail and show some cool demos. So 5 features to look at today. So moving into the first one, hardware overlay support. So today, for games, frame rate is king. Depending on the type of game, you're either going to want to hit 60 frames a second, if you're a racing game, if you're a first-person shooter, or you're going to want to hit 30 frames a second, if maybe you're a top-down RPG where frame rate is less important. And the most common way that games achieve that today is they allow the user to adjust the resolution that you're playing the game at. So if you open up a new game, you go to the settings menu, you change the resolution, and the screen flickers a whole bunch, and then you're running at a lower resolution, and the game is rendering directly to a back buffer sized at that resolution. So it's a good solution, but there are a few drawbacks associated with changing the resolution. The first is there's GPU overhead when you're changing the resolution in a composited environment. In composited environments that you're now seeing across a wide variety of platforms, the app doesn't own the display mode anymore. The compositor does. So if the app wants to render at a lower resolution, for example, the app will render to an intermediate render target and then do a separate draw operation and actually blow that up to the actual full back buffer. So there's GPU overhead, but there's also a loss of fidelity. So if you're rendering at a lower resolution, what you really want to do is you really want to render the 3D content, the really expensive content at that lower resolution. But you really want to preserve the kind of cheap, easy to render content at a higher resolution. So in Windows 8.1, we're introducing new APIs that allow for efficient, targeted scaling using the capabilities of fixed function overlay hardware. So when we talk about overlay hardware, there are kind of 2 categories of capabilities that these platforms have. The first is scaling. So as you can see, we're rendering to basically a less than native resolution of the screen. And the fixed function overlay hardware can scale that up without taking any GPU resources of its own. And it does so in a really high quality interpolation. So there's more time for the app to do its real rendering, and then the scaling happens for free. But beyond scaling, this overlay hardware can also do composition. So we're introducing the ability for an app to render to multiple render targets and have those composed together with full alpha blending for free by the overlay hardware. And again, on mobile SoC platforms, composition is a very bandwidth-intensive task. So by moving this to overlay hardware, an app can save a lot of time and leave more time for actual real rendering work. So we've designed the API to be scalable. There's different types of apps that need different levels of overlay usage. So this feature, you can implement it in very simple ways or very powerful ways. So the first way we're going to show is static scaling. This is a great option if your app has a very consistent workload and at startup just wants to change the scale factor to something that's going to be fixed for the entire lifetime of the app. So as you can see here, we render game content to a swap chain that's smaller than the native resolution of the screen, and then the overlay hardware blows that up to the display for you. So again, great if the scale factor is known up front and will not be changing. With this option, you cannot change it on the fly without a lot of work. The way this actually works is you set the physical properties of the swap chain to be the width and the height you want to render at, and you pass in the DXGI scaling stretch flag, which tells the system to stretch the content up to the size of the window. And so we've been talking a lot about overlays, but something important to note is if overlays are absent, if you're running on maybe older hardware that doesn't have this capability, the system will automatically fall back to using the system compositor to rely on the GPU to do that scaling for you. So you'll get kind of the best case scenario either way. You'll either get the overlay hardware or the system would do what you would have done anyways and scale it up for you using linear scaling. So let's give a quick look at what the code actually looks like for this. As you can see, all you have to do is set the width and the height to something smaller than the screen, pass in the DXGI scaling stretch flag, and create the swap chain. And that's it. The rest is done for you. You simply render to and present that lower resolution. So that was static scaling, a very simple way to take advantage of overlays. The second capability we're kind of introducing is dynamic scaling. So we're introducing the ability for the app to easily change the scale factor at runtime without calling DXGI swap chain resize buffers. So an app can change the resolution it wants to present at in a very performant, easy way. And the way we do that is we allow the app to render to a subset of the swap chain and then tell the system what part of the swap chain it wants to present from and scan out. So the way this looks is, well, before we go to that, this is very useful for dynamic workloads. If you have a game where you want to maintain a constant 60 frames a second speed, maybe if you start to render more complex content on the screen, you can lower the resolution by 5 or 10% and make sure you keep that constant frame rate. And you can do so without glitching the system or resizing any buffers. So the way this actually works is we're introducing a new API on IDXGI Swap Chain 2 called set source size. And all this API does is take a width and a height parameter that allows the system to know what part of the swap chain the app is rendering to. So as you can see in the diagram, we have the game rendering to the top left corner of the swap chain, and that's the actual part of the swap chain that's being presented to the screen. And again, that happens with overlays. So looking at the sample code for this, what you're going to want to do is create the swap chain at the maximum size you're ever going to want to render at. So this API specifies a subset of the existing swap chain to present from. So in this case, we're creating the swap chain at the full width and height of the screen. We're passing in the DXGI scaling stretch flag, and we're creating the swap chain as a normal. Then, depending on the app's logic, the app might want to reduce the scaling or increase the scaling if the frame rate gets low, or if, for example, if there's a lot of movement on the screen, or it's more important to maintain a high frame rate than it is to render at exactly native resolution. So it's kind of dependent on the app. But the app calls this API and then renders to that part of the swap chain. You might want to change the viewport, for example. And then you present, and that's it. There's no kind of synchronization or race conditions here. Set source size takes effect on the very next present that you call. So nothing to worry about with that. So we actually have a quick demo to show this capability. We have one of the new Qualcomm devices up here that has built-in support for hardware overlays. We're going to switch to that. So what we have here is we have a simulated workload. This is a really great piece of hardware. It doesn't have any trouble rendering a cube. We're actually doing a whole lot of clears behind the scenes. But what you see here is we're rendering the resolution at 1920 by 1080. And we're seeing that we're not able to hit 60 frames a second. We can only get 20. And maybe for this scenario, we really want to move the resolution down a little bit so that we can hit the frame rate we need to. So we're using the set source API right now to dynamically change the resolution that we're rendering at. You can see the resolution number change at the top left. And as we go down, you can see, okay, we're at 30 frames a second. Okay, now we're at 60 frames a second, no problem. And the cube looks okay. For that scenario, maybe that resolution is the preferred way to go versus running at 20 frames a second. But you'll notice that the text, the kind of HUD, the high-frequency data, starts to look really aliased and starts to look pretty bad. So it'd be really great if we could maybe render that information at a high resolution while rendering the 3D content at that lower resolution. So we can do that, and to do so, we're introducing what we call swap chain composition. We're introducing the ability for an app to create a second swap chain to render content to different swap chains, have those swap chains sized independently, allowing the app to render the 3D content at the low res and maybe the really easy but important 2D content at a high res. So what this looks like is you can see a game that renders its 3D content to the smaller swap chain while doing the important 2D content to that top swap chain. And then the overlay hardware composes those together with full alpha blending for free without taking any GPU resources. So it's a really powerful way to kind of get the best of both worlds in terms of visual quality with your app. So as you can see, we have the diagram set up here where you can have two swap chains sized independently. It's blended using pre-multiplied alpha. So we have full alpha blending. When you're only dealing with one swap chain, you kind of don't have to worry about the alpha channel. It can mean whatever you want it to mean. In this case, the alpha channel for the top swap chain is blended completely using the pre-multiplied space. So you're going to want to multiply the color channels by the alpha channel using your blend state before you kind of compose those together. So the way this works from a code perspective is you create your bottom swap chain just like you do today, as we saw earlier. Then what the app should do is check to determine whether overlay support is available on that platform. We'll kind of come back to what that means. And then they can create a second swap chain. So you can see we have a new flag here called DXGI foreground layer. And what that flag does is it tells the system to allow a second swap chain to be created using this blending. And once you've created that second swap chain, it's a real swap chain. You can present them totally independently. You can render to them totally independently. There's a lot of power that comes from that. So let's go back to the demo and find out what swap chain composition looks like. Okay, so we have the ability in this app to change dynamically between a single swap chain and dual swap chain modes. So in this case, we're now running with two swap chains on the screen. You can see that the text is now very clear. We're rendering the text at a native resolution to the top swap chain, and we're keeping the 3D content at that lower resolution on the bottom swap chain. So kind of a lot of power with that. You get the best of both worlds. So kind of taking this into the real world, we've worked with some Microsoft developers who are responsible for Reckless Racing, one of the new titles that was released with Windows 8, to see how their game could implement this API and how they could take an existing title and move it to this rendering model. So what we have here is Reckless Racing running on two different swap chains. At the top, you can see we have a frame rate counter and the resolution that the bottom swap chain is rendering at. And as you can see, as we drive along, everything looks great. If, for example, though, we come across a really tricky part of the track where it's very visually intense and we want to maintain 60 frames a second, we have the ability to scale that down dynamically. So you can see the resolution is getting lower and lower, and now it's very visibly jagged, where we're rendering at a very low resolution on the bottom swap chain while keeping the top content very clear. So one of the really important things to note, though, is when rendering at lower resolutions, the scaling quality of the interpolation that you see is very, very good. So we're actually going to go up to about 10% of the native resolution of the screen. And what you'll notice is it's actually really indistinguishable from the native resolution of the screen. And it's especially true on high DPI displays. So it's a really great way to render at a slightly lower resolution while getting a great benefit in frame rate. For example, if you're rendering at 10% of the native resolution, you're saving 20% of the overall pixels. So if you're fill rate bound, it's a really great way to improve performance. And the Reckless Racing team who worked on this, they were able to take, again, an existing app that was already created and move it to this new API without much work. And that's because you have two real swap chains that you can render to totally independently. And we think there's a lot of power with that. And we think this is a great way for apps to improve their performance on mobile systems. So let's go into some of the best practices for swap chain composition. Again, when you have overlays, the scaling and the composition is done for free. You're not taking any GPU resources by doing this, what's really an advanced composition blending pass. When overlays are not available, as with scaling, the composition will fall back to the GPU. So you still have a great experience. Your app will work just fine on any hardware without these overlays. But our recommendation is to only use two swap chains when you're running on hardware that has overlay support. Again, doing a full composition can be very bandwidth intensive. And if you're running on a platform that is where there's not tons of bandwidth, you're definitely going to want to only use a single swap chain. And to determine that at runtime, we have a new API on the IDXGI output called supports overlays. And when that's true, the app should definitely use two swap chains. But when that's false, the app should just fall back to a single swap chain path. So kind of beyond best practices, there's a lot of advanced usage and a lot of kind of power that comes with this API. So the swap chains first can be presented totally independently. If you have a game where the bottom swap chain has a 3D world and it's rendering every frame, that's great. But if you have a HUD where maybe the time is only incrementing once a second, you don't have to render every frame. You can render once a second and present once a second and render in the most efficient way possible. Either swap chain can be dynamically scaled. So in the examples we've shown the 3D world is generally on the bottom swap chain, and the HUD, the native resolution content, is generally on the top swap chain. But the app has complete power and complete choice to do what it sees there. Maybe you have a game where you want to render the skybox, kind of lower resolution textures, on the bottom swap chain, which is a super low resolution, and you might want to do that to save bandwidth. And then maybe you want to render the rest of the 3D world on the top swap chain at a medium resolution. So again, depending on the game, there's a lot of kind of advanced capabilities you can use with that. This API, as you saw, was for core window store apps only. So this is for core window swap chains only, which are what are available in the Windows Store environment. And it opens up a lot of new rendering possibilities, new rendering scenarios. So it's actually a really great way to achieve full multi-threaded rendering with Direct3D. So if you have a lot of draw calls in your app, and your app is being bound on the CPU usage from those draw calls, dual swap chains is actually a really intuitive way to perform full multi-threaded rendering. You have one D3D device for the bottom swap chain that you can render from on one UI thread, and then you have a separate D3D device for the top swap chain that you can render to on a separate thread. And the CPU side of those draw calls will be completely parallelized. The GPU still will only process one of those aspects at a time. So we think this is a really great way for apps to improve their performance on mobile platforms in a very, very visually compelling way, kind of get the best of both worlds with 3D content and with high-frequency 2D content. Okay, so moving on, the next feature we're going to be talking about is runtime shader modification. So changing shader behavior at runtime is important. Games sometimes want to optimize out inapplicable code paths. If you have maybe a variable amount of light sources in your shader, if you have a variable amount of, or if you have different types of textures or surfaces that can be used, a game would like to customize a shader for a particular scenario in the app. So we've heard a lot of feedback on the fact that the HLSL compiler was not available in the store environment. And we're really pleased to say that it is now available. It's included in the System32 directory, so the app doesn't need to include the DLL at all. It'll just be there on any Windows 8.1 system. But compilation is great if your app needs it. If you have an existing app that's running on the desktop that uses shader compilation, you can now move that to the store environment with no problem. But compilation of all types is inherently slow. If you want to change a shader in the middle of a level, it's not a great answer because it takes a lot of time to compile these new shaders, and you need them to be really responsive. There are a few other kind of answers to that. Maybe you compile every possible permutation of your shader, and you have 100,000 shaders on the disk, and you load up the one you need for that scenario. But that's not always practical if you have too many different possible combinations. Another option is maybe to have dynamic branching in the shader, where you have a bunch of if statements and you have a constant buffer that kind of controls the flow of that. But again, you're throwing away performance on that dynamic branching. So can we go further? And the answer is yes. We're introducing a new API that we call HLSL shader linking. And what this does is it allows you to compile shaders ahead of time offline into individual chunks and then link them together at runtime in a really easy, performant way. So useful for changing shader behavior at runtime. Again, if you want to adjust a shader to a particular environment and to a particular rendering scenario, or for library-style shader usage. Or if you have a photo rendering app, maybe you want to have a little shader fragment for brightness and then for saturation and then for color temperature. You don't want to have all these different shaders floating around, or you don't want to have to render to intermediates and use one shader per render pass. So a lot of power there. And the great thing is that this is available on all feature levels, on all platforms running 8.1. So it's guaranteed to be there, and you can definitely design your app knowing that it will be available on any platform you try. So let's show a quick demo of what this actually looks like. So we're running, we have a quick example we made that allows the app, that allows an app to take advantage, that shows what shader linking looks like in real time. So we have a very simple pixel shader currently right now. All we're doing is sampling from texture coordinates, and you can see the result on the right. And what we can do is we can toggle the behavior of that shader to change. Maybe we want to add a lighting effect. to that. And what you can see is the actual shader bytecode on the fly changes to what you see in the middle here. So you might be wondering, okay, how performant is this? How much overhead are we introducing by allowing different parts of shaders to be linked in together? And we're actually able to keep the overhead extremely low. We do this linking very intelligently. So for example, if we look at the grayscale effect, you see toggling grayscale only makes everything look gray. What you can see is toggling it on and off. We're only adding a single dot product instruction to the shader bytecode. So you'll notice that the row below that dot product, we're changing the register we're looking at. So we're kind of dynamically adjusting that so that adding functionality only introduces the instructions that you absolutely need to. And when you look at the actual performance you can get from shading versus compilation, it's dramatically improved. So we've added a benchmarking mode. And what you can see here is that shader linking is 8 times faster than runtime compilation, on the order of a millisecond versus 8 milliseconds, even for this simple shader. And with shader linking, you'll have the cost stay relatively constant even as you introduce more and more complicated shaders. With compilation, that's just really not practical if you want to adjust that in real time. So again, a really powerful API to adjust behavior. It's going to be available on all platforms running Windows 8.1. So we want to give a quick overview of what the actual API surface for this feature looks like. So we're introducing a new HLSL compile target called lib50, and what you can do is point the compiler to an existing or new shader file, and it compiles the shader file in such a way that you can then link against it in runtime. So once you've created the shader file you want to link against, there's a new D3D create function linking graph API that's used to create conceptually your function linking graph that contains all the logic for which functions are called in order, how values are passed between different shader functions. Once you have your shader graph, one of the really important APIs is call function on the shader linking graph. You then call it to any particular shader fragment, export function in your shader code. The other kind of important API is pass value, which allows you to change how you pass values between different shader fragments. And finally, once you have the graph set up in the way that you'd like, you actually create the shader linker, which takes the graph and outputs shader bytecode that you can consume like any other compiled shader bytecode that you might load from disk today. So we think that this is a really powerful API and a great way to change shader behavior at runtime in a really performant way. So the next feature we're going to talk about is mappable default buffers. So in Windows 8.1, actually I have a clicker, I think. In Windows 8.1, reading data back on the CPU involves a default to staging copy. In Direct3D, there are different types of resource usage you can create. You can create default resources, which can serve to be the output of a compute shader, but can't be read by the CPU. Or you can create staging resources that can be mapped for reading by the CPU, but can't serve as the output for a compute shader. So what that involves is you basically have to have this kind of weird copy where you maybe render to a default buffer and copy that to a staging and then map the staging buffer. So it's a performance issue for compute shaders when you want to really optimize all the bandwidth you can getting data to and from the GPU. So Windows 8.1 allows default buffers to be directly mapped, what we're calling mappable default buffers. So as you can see, the new code path can be you render a compute shader to a default buffer, and then you map that default buffer directly on the CPU, saving that copy operation. The way this works from an API perspective is you use existing CPU access flags that you might use with dynamic or staging resources. At resource creation time, you simply create your default buffer, and then you pass in the CPU access flags for read, write, or both. You can do read, write, or both. For this release, we're really targeting direct compute scenarios, which means we're limiting this to buffers only, no texture 1D, 2D, or 3D objects. Direct compute objects, direct compute shaders use buffers very frequently, so we think it's a great solution for that. It's available with new drivers on hardware that can access GPU memory directly. So we enable this, we report that this is available to apps when you're running on hardware that can kind of optimize for direct GPU access. And when you're running on hardware that doesn't have this capability, there's a very simple fallback path. You simply create a new staging resource and perform the copy that you would have to today and map the staging resource. So it's a great thing to take advantage of if you're on new hardware, if you have compute shaders that you're using for physics calculations or anything of the sort, where you need to read data back on the CPU. So the example code for this looks like, we have a new enumeration on check feature support, D3D11 options 1, and one of the properties on that struct that's returned is map default buffers. So if that's true, this functionality is available, and assuming the app created the buffer with the right CPU access flags, you can simply call map on it and access that data on the CPU. Else, simply create a staging resource and perform that copy like you would today. So it's a very kind of simple A or B path to take, but you can really benefit from performance. You can really get better performance when you're running on hardware that supports this. So the fourth API we're going to be showing is what we call the low latency presentation API. So what we call latency is the time between user input and the result on screen. And low latency is key for user satisfaction. Especially in a touch environment, a user expects when they touch the screen, they expect something to happen, and they expect something to happen very quickly. If they're dragging an object around, they want to see it stick to their finger. If they're panning around a scene, they want it to feel responsive. If your latency is too high, the game doesn't feel like it's responding to the user. It feels like something's wrong. The challenge is it's very difficult to know exactly how to render to achieve the lowest possible latency. This is possible today. You can kind of hack together a solution using frame statistics, doing like weight on VBlank and such, but it's very difficult and it's very brittle. So what we wanted to do is introduce a new API that makes it really easy for apps to optimize their rendering for latency. So, new low-level API on IDXJ swap chain 2 called get frame latency waitable object. And what this API does is it returns a 132 waitable object that the app can then wait on, and the system kind of promises it'll signal that semaphore when it is best for the app to render. So to get at the new API, you create a swap chain with a new flag that kind of opts you into this new rendering model. And the handle is signaled exactly when the app should perform the rendering operations. Not too early, not too late. It kind of abstracts away that difficult work for the app. So the way we expect this to work is the app will call wait for single object EX on the handle. Once that unblocks, it means it's time to render. It means the system is ready for new rendering work. So the system should process any latency-sensitive events. It should render the scene, and it should call present. Except this time, present will not block anymore. It will go right through and go back to waiting on the single object if the app so chooses. So in addition to lower latency, this API actually gives you a lot of flexibility in how you want to set up your rendering loop. So today, present kind of blocks whether you want to or not. It can kind of get in the way of how the app wants to lay out its rendering code. You now have a handle that you can wait on wherever you want in the code. You can synchronize this with other thread synchronization objects. Maybe you want to call wait for multiple objects. So kind of a lot of power there. So let's give a quick demo of what this actually looks like. So I'm going to plug in the mouse to this computer, and we're going to switch to a example we created to show what this can look like. Okay, so what we have on the screen here is we have an example that is presenting using the Windows 8 behavior in terms of presentation. You can see the latency is about 46 milliseconds, just under 3 frames of latency. And this is when we've chosen to set the maximum frame latency down to 1. You might recall that there is an existing API that lets you choose the amount of latency you get. The default's to 3. If an app wants to lower the latency, you can call IDXJ swap, IDXJ device set maximum frame latency and set that to 1. So we've set that to 1, and this is actually the best latency you can achieve on Windows 8. And what you can do, what the example can do, is we can follow along the mouse cursor with this circle. So the app tries to, get the position of the mouse cursor and render as quickly as it can to, simulate any sort of game environment. And as you can see, the mouse cursor can get, a little bit ahead of the circle without too much effort, without going very fast. So we've built the example to now take advantage of the new the new low latency API. So hitting the spacebar, we're now changing to this new presentation mode. And the latency figure you see on the screen is real. We're using frame statistics to determine the delta between queuing up these rendering operations and then being executed on the screen. So you can see we're actually getting less than a frame of latency just less than a single 16.67 milliseconds of latency. And when you start to interact with the scene, you notice that the circle dramatically is closer to the mouse cursor. It's very difficult to get ahead of that. And that's because you're rendering with 2 less frames of latency. And that's really tangible and really noticeable if you have an app where the user is interacting with touch or the user expects expects a low sort of latency. So going back again, you'll see you'll see a greater distance between the circle and the mouse cursor. And if you're actually operating this, you can definitely tell a difference. Going back to the new mode, you can see it's very, very smooth and very low latency. So the way this looks like from code is you create the swap chain with this new flag that opts you into this new presentation model. You create the swap chain for core window. This is, of course, available for H1 swap chains as well. Once you've created the new swap chain, you call get frame latency waitable object, and that returns you the 132K handle that you can then use for your thread synchronization. So in your app, you might have a while true loop, while window is visible. You're rendering in a tight loop. The way the app should work is just wait on this object. Once that unblocks, render, present, and again, present will go right through, and you would then again wait on this object for the next time. And the system will kind of keep the app rendering at the frequency it should to ensure too many frames don't get queued up. And also and also time that out to make sure you're not rendering too late where you don't have enough time to actually render a frame and you start to drop below 60 frames a second. So the 5th feature we're going to briefly talk about is tiled resources. And this is what you saw Antoine demo at the keynote this morning. So gamers want immersive, high-detail worlds. The problem is it takes a lot of resources. It takes a lot of memory to draw these huge resources. So conceptually, if you have a mountain on the screen and you want to use a single texture to fill in the mountain, you have to load the entire texture onto GPU memory, even if only part of the mountain is visible. So what tiled resources really is it's the ability to load in only the parts of a resource that you really want to, or that the game really needs to. So in that case, you can load in the part of the mountain that's visible according to the game's own logic. And you have a lot of flexibility with this. You can load in data in 64 kilobyte chunks. So you can allocate a 16K by 16K resource and only load in the parts that the app needs to for a given scenario. And the smaller overhead means more resources left for detail, more resources left for the actual game itself. So we're going to go into quite a lot of detail on this feature in a dedicated talk coming up actually right after the session. But briefly, the way this works, the power that kind of comes from this feature is we're allowing apps to indirectly manipulate the hardware page table on GPUs. So the GPU then is able to, in its texture filter unit, to sample for free between physically disjoint parts of memory. So there's a lot of kind of power with this. And really importantly, it's a feature that's available on hardware that's already in the marketplace today. It's going to be available on all hardware, on many hardware platforms going forward, but it's already available on, I think, tens of millions of hardware already out there today. And it's optional for feature level 9.0 and higher. So this is another one of the properties on the new check feature support API that your app can check for. So we'd really highly recommend that you check out this next talk. We have a lot of cool demos and a lot of cool example code to show the scenarios and ways that your apps can take advantage of this API. Okay, so let's give a quick summary of what we looked at. So there are 5 new features. First, hardware overlay support, optional across all feature levels. You need to check for support if you want to use a composition. Otherwise, the scaling will be done for you for free, or for free with overlays, or it will be done in a really efficient manner on the GPU if necessary. Shader linking, available across all feature levels, a great way to change the behavior of shaders at runtime in a really performant way. Runtime compilation is there when your app needs it, but shader linking is a great performant alternative to that. Third, mappable default buffers, a new optional feature that will be broadly available on WDDM 1.3 drivers. The new drivers are being released today. Fourth, the low latency presentation API, available across all feature levels, something your app can definitely take advantage of. And fifth, tiled resources, optional for feature level 11.0 again, but available on hardware that's already shipped today, going back some distance in some cases. So really cool. New interfaces to kind of power those features. We have the next version of ID3D11, ID3D11 Device 2, ID3D11 Device Context 2. You're going to see tiled resources primarily on that API. And of course, we've updated check feature support with new enumerations to return support for these features. ID3D11 function graph, that's for shader linking. ID3D11 swap chain 2, that's where you're going to see the set source size API to vary the resolution that you're rendering at on the fly. You're also going to see the get frame latency semaphore in terms of actually using the low latency representation API. IDXGI output 2, another iteration of that. That has the supports overlays API that you can use to determine whether the system has overlay support, whether you want to use 2 swap chain composition. And finally, IDXGI device 3. That has the new trim API that your app should call on suspend for any D3D device you directly create. An important point to note is if you're a WWA or if you're relying on a framework that creates a D3D device for you, we're already going to take care of that in the system and call that on your behalf. But any D3D device that the app owns, the app should call trim on that interface. We have a number of SDK examples available to show how these features can be implemented. Everything from overlays, which is similar to the demo you just saw, shader linking, mappable default buffers, the low latency presentation API, and tiled resources. You actually get to see the Mars demo running on your computer that you saw from the keynote today. So definitely check these out. They're really a great way to kind of see how the APIs work, see how the functionality works, and how to implement it in your own app. So in summary, there's some great improvements to the Direct3D Runtime API. Again, we spent a lot of time, spent a lot of effort improving the kind of core functionality of the API, making existing APIs faster, moving functionality down to new feature levels, and your apps will take advantage of that just by moving to Windows 8.1. But you can use new APIs to take that performance even further. So overlays are a really powerful way to render at a slightly lower resolution, but for it to still look great on the screen, again, without any GPU overhead. You're doing a really advanced composition pass that results in a great experience without any GPU overhead. So the kind of call to action here is to use the new features to make your app as performant and responsive as possible. Use these new features to render in new ways so you can allocate more resources to the actual detail and rendering in your app. So we have a number of related build talks to Direct3D and gaming. DirectX, I'll call out 2 in particular. DirectX tiled resources, that's the deep dive on the new tiled resources API on how you can use it for scenarios in games. And also I want to call out actually a talk that we gave in 2012 on performance tips for Windows Store apps using DirectX and C++. The theme for today's talk was all about performance, using the new APIs for performance. But that talk goes over kind of general best practices your app can use to achieve the best possible performance if you're on a power-efficient or bandwidth-limited platform. So a lot of really great stuff there, and we definitely encourage you to check that out. So that's all the content we have today. Thanks for coming. We now have time for questions if anyone has any questions to ask.
So on the pin memory, shared memory,
Yeah.
is that the only API I have? I noticed Intel did something at, I think it was a game developer conference. They had their own little hack to do to.
For direct GPU access. So.
Yeah, they just sort of, I think they showed, I think it was a 2x2 tiling pattern. They would let you map. Is that something you guys officially support, or is that something they just off doing on their own? Or?
Well, we designed this new API to be broadly available across all hardware platforms.
Yeah.
Intel is free to create new features that can take advantage of their hardware.
Yeah.
There wasn't a direct link between these two features, though.
Oh, okay. But do you guys have any sort of official way to do a texture 2D?
Not at this time.
Okay, cool. Oh, and in the the tiled stuff, is that just one of the AMD stuff, latest AMD cards?
We can't go into hardware specifics, but expect it to be available across a variety of hardware manufacturers.
Yeah, I know that guy, and they put it in their last generation hardware. But
Okay, thanks. Any other questions? Feel free to use the mics.
Yeah, I just wonder, the new features are available for 8.1. How about the 8.1 desktop? Are they the same DX?
Yeah, so it's the same. Thanks for your question. The question was, all the features we talked about today, are those available for desktop apps as well as store apps? And the answer is yes. All the features you saw today will be available. The sole exception is the core window swap chain API that allows you to create 2 swap chains at the same time. But all the other features are using the same D3D runtime, and you can take advantage of all those APIs and functionality improvements on kind of both environments.
Probably you things that you talked today, but in general, in DXGI 1.2, does it support stereoscopic capturing, desktop duplication APIs?
Stereoscoping and capturing?
Capturing, yes.
We can actually talk about that afterwards. I'm not positive that it does.
Okay.
Okay, any other questions? Okay, well, I think that's all we have then. Thanks very much for coming.